Hi everyone, this is Maverick Paul, the chemistry guru. Now, in this video, we want to run through the third portion involving 2022 A-Levels H2 Chemistry Paper 1, starting from question 21. The alkene 2,5-dimethyl-hexa-1,4-diene reacts with 2 moles of HBr to give X as the major product. So we want to determine the major product. Since this is an alkene, adding HBr, which is electrophilic addition reaction, topic tested in this question obviously will be involving alkene reactions. So first thing we do is we draw out 2,5-dimethyl-hexa-1,4-diene, which looks something like this. Fairly simple. I'll have 2 alkene function group. 1-ene double bond is between carbons number 1 and 2. 4-ene double bond is between carbons number 4 and 5. If you put in HBr, we know that this is an electrophilic addition. And since we are adding HBr, which is 2 different things, hydrogen and bromine, an asymmetrical reactant, add it to my alkene, which is also asymmetrical, then we have to consider Markovnikov rule. Markovnikov rule will help us determine the major product. Markovnikov says that hydrogen joins to the carbon with more hydrogen to give me my major product. So for each of these alkene, I just need to consider which alkene carbon has more hydrogen. Then according to Markovnikov, hydrogen joins to the carbon with more hydrogen, and from there I'll be able to deduce the major product. So it's fairly straightforward. Involving my 1-ene, if you look at the 2 carbons, carbon number 1 has 2 hydrogen, carbon position 2 has no hydrogen. According to Markovnikov, hydrogen joins to carbon with more hydrogen, which is carbon position 1, bromine joins to carbon 2, so that will be the major product for your 1-ene. Then if I consider my 4-ene, double bond between carbon number 4 and 5. Carbon number 4 has 1 hydrogen. Carbon number 5 again has no hydrogen. Again, carbon number 4 has more hydrogen. According to Markovnikov, hydrogen joins to carbon number 4 with more hydrogen. Bromine joins to carbon 5. This will be my major product. So we will expect involving my product, your major product will be something like this. If I consider this straight chain 6 carbon, my bromine is attached to carbon position 2 and bromine is attached to carbon position 5, and I also have a methyl group attached to carbon position 2 and your methyl group attached to carbon position 5. So what we will have to do is we will have to compare the major product that we have deduced, and I also have to compare this with my 4 options and see which is my answer. And for each one of them, essentially we have to consider comparing the structural formula, see whether they're the same guy or not. So what I've done here is to make it very clear, for each of these compounds, I just draw out the carbon arrangement and expand out all the bonds. Involving A, I have straight chain 6 carbon. Methyl group is on carbon position 2 and position 5. Bromine is also on carbon 2 and carbon 5. And therefore, A is my answer because it's exactly the same as what we have predicted. Now, how about B? Involving B, if you try to draw out the carbon chain, expand out all the bonds, what I have is my bromine is on carbon 3 and carbon position 5, which is not what we want. I want bromine to be on carbon 2 and carbon 5, so B is wrong. Involving C, this is also problematic because the position of your bromine will be to carbon number 2 and carbon number 6, and which is wrong. And finally, involving D, the position of your bromine is to carbon position 3 and carbon position 6, which is also wrong. So basically, if I run through my 4 options, my answer to this question will be A. Now, question 22, the following scheme represents the result of a hydrolysis reaction. We have this chloro compound reacting with OH minus. I get 50% of this guy and 50% of the other guy. Which statements about this reaction is correct? Number 1, intermediate in the reaction has a plane of symmetry. Number 2, there are 2 intermediates in the reaction which are mirror images of each other. Number 3, reaction proceeds via SN2 mechanism. So we want to see which of these statements is correct. Since we are talking about halogenoalkane, topic tested should be under halogenoalkane, targeting the mechanism SN1 versus SN2 mechanism. Now what I've done is I've drawn my products again, but I put it in such a way where it is easier for me to visualize that there are mirror images of each other, 50% of this and 50% of that. So if I put them one on top of the other, it is easier for me to show, or it's easier for me to see that they are actually mirror images of each other. So the mirror plane is here, and I have one group on top, one compound at the bottom. The CH3, both of them are towards you, they'll mirror each other. hydrogen, both of them are pointing away from us, they mirror each other. OH group, they also mirror each other. So basically, I have a racemic mixture, and if it is a racemic mixture as a product, we will expect mechanism to go by SN1 mechanism. SN1 mechanism, if my product, I have a chiral carbon, we will expect this guy to be racemic because of the intermediate that is being formed, and we're going to talk about this along the way. Now, statement 1, intermediate in the reaction has plane of symmetry, which is true. Why is that the case? SN1 mechanism is a two-step mechanism. Step number 1, you break the CCl bond. Both electrons go to Cl, which is a partial minus charge. You form a carbocation, and you end up kicking out a Cl minus. Now remember, my carbocation, it is trigonal planar. Carbocation is only bonded to 3 groups. sp2 hybridized, shape with respect to carbon is trigonal planar. If it is planar, then there will be a plane of symmetry. The plane of symmetry is just lying along all the atoms with respect to my sp2 carbon. So the CH3, the hydrogen, and the benzene carbon will all be lying along the same plane. And that is the plane of symmetry. And because it is flat, because it is symmetrical, then both sides are equally exposed. On top and at the bottom, they're both equally exposed. So therefore, when the OH minus comes in, it can attack the top part of your carbocation 50% of the time, and it can attack the bottom part of my carbocation 50% of the time. That's why I'll end up with 50% and 50% of my two products, which gives me my racemic mixture. It's because of the sp2 carbon, which is planar, and because of this plane of symmetry, then it can be attacked from both sides to equal extent, and this will give me a racemic mixture which is optically inactive. So number 1 is okay, number 1 is correct. Now how about statement number 2? Statement number 2, there are two intermediates in the reaction which are mirror images of each other. It is not true because there's only one intermediate. The reason why I'll have two products is because this carbocation can be attacked from two different ways to the same extent, and that's why we will end up with two different products. It is not because I have two different intermediates, that's why I have two different products, but I have the same intermediate that can be attacked in two different ways, then you give me two different products that are mirror images of each other. So if you're familiar with SN1 mechanism, then definitely we know that statement number 2, it doesn't make sense. Statement number 2 is totally wrong. Number 3, reaction is via SN2. This is clearly wrong. Involving the mechanism that forms a carbocation that ultimately gives me a racemic mixture, the mechanism has to go by SN1 mechanism. SN2 mechanism is a one-step reaction, and I will not end up with a racemic mixture if it goes by SN2 mechanism. Out of the 3 statements, only statement number 1 is correct, so answer to this question will be B. Now question 23, we have 4 compounds, warm with sodium hydroxide in aqueous ethanol, acidified with dilute nitric acid before shaken with aqueous silver nitrate. Mixtures are then shaken with ammonia solution until there's no further change. Now this is a fairly standard test for halogenoalkane. What we do is we do a reaction with NaOH with warming, that is a nucleophilic substitution, basically to kick out the X minus for precipitation. Then we do acidification using nitric acid. Adding silver nitrate is to try to precipitate out my halide. Then if you shake it with ammonia, we see whether we can dissolve the silver chloride or bromide or iodide. Based on solubility, we can decide whether this is a chloride, bromide or iodide. And I have 4 compounds here, and the question is asking how many mixtures will produce PPT with silver nitrate and how many of them actually will remain when you react this with ammonia solution. So what we will have to do essentially is we have to consider each one of them. What happens when you react with sodium hydroxide, then when you add precipitate, will there be a halide that's being kicked out or being substituted? Then which one of them would I get a precipitation? And then from there, when you add ammonia, which of these precipitate ultimately will dissolve? So let's run through this part by part. Now, the summary is here involving each of these components. All right. First thing is I react with sodium hydroxide equals warm. We will assume that condition is drastic enough for nucleophilic substitution to occur. Remember, when you do nucleophilic substitution, only a halogenoalkane will undergo nucleophilic sub. If you have a halogen that is directly attached to benzene, the lone pair of your halogen will interact with benzene, and the resonance stability will be extended to your CX bond, and you're not able to break that CX bond. So if you have a chlorine attached to benzene, that bond is stabilized by resonance. You're not able to break that bond. Same goes for your bromobenzene. Same goes for your aldobenzene. So none of these guys, when the halogen is directly attached to benzene, we will not be able to break that bond. It doesn't undergo nucleophilic substitution reaction. There's no PPT kicked out if it is involving a halogenobenzene. All right. Now, the halogenoalkane that can undergo substitution is when your halogen is attached to my alkane carbon. In this case, this first guy here, you have your aldene that is attached to your alkane carbon. So yes, this guy can undergo nucleophilic sub to form my alcohol and to kick out my I-. Involving this chloroalkane, it can also undergo substitution to form my alcohol and kick out my Cl-. Aldobenzene, nothing will happen. As mentioned previously, this guy is stabilized by resonance. I'm not able to break this bond. This aldene is attached to alkane carbon. So same thing, it can undergo substitution to kick out I- and to form my alcohol. So next thing is when I throw in AgNO3, which one of them I'll have a precipitate. As long as I have a halide, chloride, bromide, iodine, I'll be able to get a precipitate. I- is here. For the first guy, I'll have a AgI-PPT. Cl- is present for the second guy. I'll have a AgCl precipitate. Third one, there's no halide that is being kicked out. No precipitate for the third guy. Fourth guy, I have an I- aqueous. And therefore, I'll have an AgI precipitate. So finally, if I consider when you try to dissolve all these precipitate in ammonia, which one of them will dissolve? And actually, if we refer to the QA notes, we actually also have concept involving solubility product or group 17 concept. We understand that involving silver chloride, silver bromide, silver iodide, only silver chloride will dissolve in dilute ammonia. Silver bromide, silver iodide, the KSP is lower or they are less soluble. And therefore, if you add dilute ammonia, I'm not able to dissolve AgBr. I'm not able to dissolve AgI. Solubility for AgI is too low. And therefore, ammonia will not be able to dissolve your AgI. So if the PPT is involving silver iodide, the precipitate will remain. It doesn't dissolve. Involving the first guy, AgI precipitate will remain. Involving the second one, the AgCl precipitate will dissolve. I will not end up with any precipitate. The third one, there's no PPT in the first place. The final one, AgI precipitate will remain. So basically, to answer this question, involving which one of them will give me a precipitate produced with AgNO3, we have three of them, the first, second, and the last guy. And involving which one will give me a precipitate remaining with ammonia, I'll have two of them, both silver iodide will remain, the silver chloride will dissolve. So PPT remaining with ammonia, I'll have two of them. PPT produced with AgNO3, I have three of them. So answer to this question will be B. Question 24, which molecules rotate plane polarized light? So essentially, we want to look out for a chiral carbon. In general, if I have a chiral carbon, which is a carbon bonded to 4 different groups, I'll expect that guy to be optically active. If it is optically active, then it will be able to rotate plane polarized light, correct? So the idea is essentially that. Now, if I look at each of these guys, involving number 1, I have a chiral carbon here. So this guy is chiral bonded to 4 different groups. I'll expect this to be optically active. So number 1 will be part of the answer. Now involving number 2, number 3, number 4, what we will have to do is we will have to do some rotation of a bond, because you notice if I consider your compound number 2, for example, I actually have 2 chiral carbon. So this carbon that is bonded to bromine is chiral, bonded to 4 different groups, attached to a bromine, attached to a hidden hydrogen, attached to an ethyl group, attached to the neighboring carbon. Now the other carbon, also the same, is bonded to 4 different groups, also bonded to the same 4 groups, and therefore the carbon is also chiral. And therefore, what we will need to do is we will need to check whether is there an internal mirror plane. If there's an internal mirror plane, then even though the 2 carbons are chiral, they will be able to cancel out each other's optical activity. So such compounds, we call it a meso compound. And we actually need to do some rotation and we need to do some figuring out so that I can see whether they are mirror images of each other or not. Now, the way the question is drawn is such a way that it's not that intuitive, not so easy for us to tell. So what we will want to do is we want to try to point the bromine along the same direction and the ethyl group along the same direction. It is easier for me to decide whether is there an internal mirror plane or not. What we do is I'll rotate the yellow carbon-carbon bond. So basically what I'm doing is I'm fixing this group on top, then this bottom here, I'll just rotate it and I'll flip it over. So the ethyl group will come to the bottom. So you notice, if let's say I were to imagine if I draw a mirror plane here, then this ethyl group will mirror each other. So it's easier for me to tell is there any mirror plane or not. the ethyl groups, they will mirror each other. The bromine at the beginning, when it is pointing down, it is pointing away from you. If you rotate it up, then what happens is you'll be pointing up, but it will be towards you. You notice I have two chiral carbons. The two ethyl groups will mirror each other, but the bromine actually doesn't mirror because one of the bromine is pointing away from you, the other bromine is pointing towards you. And therefore, I have two chiral carbons with no internal mirror plane. So this guy will be optically active. So number 2 will be active because there's no internal mirror plane to cancel out each other's optical activity. Now, if I compare this with number 3, then maybe it becomes clearer. What do you mean by internal mirror plane? Same idea here. The way they put the ethyl group is not so easy to compare. So what we do is, again, we rotate the carbon-carbon bond, which is this yellow carbon-carbon bond. So once we rotate it, the ethyl group will be pointing down, which will be here. Mirror the other ethyl group on the other side. Then the bromine, at the beginning, it is pointing down towards you. You rotate it up, it will be pointing up, but it is pointing away from you into the paper. So you notice what we have is these two carbons are chiral, bonded to 4 different groups, but they happen to be mirror images of each other. I have ethyl group, which is a mirror, bromine, which is pointing away from you for both of them, which is a mirror. It must mean that I'll have 2 hydrogens, which is pointing towards you, which is also mirror images of each other. So this is my meso compound. 2 chiral carbon, but because of an internal mirror plane, they will cancel out each other's optical activity. So this guy will turn out to be optically inactive. This is my meso compound. This is my meso compound, where you have 2 chiral carbon with an internal mirror plane. They'll cancel out each other's optical activity. This is the one that is optically inactive. It doesn't rotate plane polarized light. Now finally, involving number 4. Number 4, what we have is, if you try to do the same as what we have previously, what we do is we rotate the yellow carbon-carbon bond. If you flip these 2 groups around, then same thing, my ethyl group will mirror each other. Now this bromo group at the beginning is pointing down, pointing away from you. You rotate it, then it'll be pointing up, pointing towards you. And ethyl group will mirror, the bromine will mirror, and therefore the hydrogen must mirror each other. Again, this is an example involving my 2 chiral carbons present in a compound with an internal mirror plane. This is also my meso compound. This guy is also optically inactive. In fact, your compound number 4 and compound number 3, they are identical. They are effectively the same thing. Both of them are optically inactive. They do not rotate plane polarized light. So for this question, we actually do need to do some rotation of the bond. It makes it easier for us to figure out what is going on. So maybe try to spend a bit of time, see whether can we interpret, if I rotate this certain bond, then how will the compound actually look like? Where the bonds are pointing, which one is towards you, which one is away from you. We actually need to be able to figure out. Alright, so in this case, only number 1 and number 2 is optically active. Answer to this question will be B. Now question 25, we have butanone reacting in a 3-stage process to produce 2-methyl-butanoic acid. The compound is given. Which reagents could be used for the 3 stages? Now, the idea or the concept tested in this question is actually involving organic synthesis. Involving synthesis, if I have a starting reactant, how do I eventually form my product in a certain number of steps? So basically, if I compare the differences between the reactant, which is a 4-carbon ketone, and my product, if you go and count the number of carbons in the product, I actually end up with 1 more carbon. So that means I have 5 carbon. And this is a step-up process. Along the way, I know that I need to introduce 1 carbon. All right, so along the way, I know that I need to do a step-up. I need to introduce a carbon using nitrile. So what we can do is we can just consider each of these options. How about A, look at each of the stages. Can I move on? And then I form my final product. If I proceed on, follow stage number 1, stage number 2, stage number 3, see which one will give me this product. Then we can decide which of this is my answer. So let us run through this part by part. Now involving A, I have butanone. First thing is if you use corn H2SO4 heat, actually there's no such reaction. If it is a ketone, if you recall the reactions of a ketone, it doesn't react with concentrated H2SO4 heat. It doesn't take part in elimination reaction. So A straight away, it is out of the question. It's not possible for A to be my answer. Step number 1 doesn't even proceed. So we don't need to consider step number 2, step number 3. Correct? So A is definitely wrong. How about B? B is the same thing. If you have a ketone, then you go and use NaOH aqueous heat, which is hydrolysis and involving ketone based on the reactions that we understand for ketone. it doesn't undergo hydrolysis, so it is not possible for me to have any meaningful product. So B also is wrong, then we can ignore B. How about C? If I consider C, what I have is I have a ketone, HCN trace NaCN co-condition. This is a nucleophilic addition. Correct? I can add nitrile to my carbon position 2, my carbonyl carbon, convert your double bond O to OH. So I have my product here. This is a cyanohydrine basically. Step number 2, concentrated H2SO4 heat. Now concentrated H2SO4, this is an elimination reaction. I can eliminate water. I can form my alkene functional group. So I have alcohol here. I have a neighboring hydrogen to this alcohol carbon. I can form a double bond between these two carbon. So it's possible for me to form a 2-in double bond between carbon number 2 and 3. Alright, so far so good. Next one is I do an alkaline hydrolysis. Now, involving NaOH aqueous heat. I can do an alkaline hydrolysis. Hydrolysis, in principle, it is capable of converting my nitrile to an acid group, but you have to be careful because it is alkaline hydrolysis. So instead of an acid, I'll end up with salt of acid. Actually, this is close enough, but the final answer is actually not really what we want. Instead of an acid, I end up getting a salt of my acid. And let us see, involving option D, would I have a better answer? Alright, so how about option D? Now option D, the sequence is here. Step number 1, this is a nucleophilic addition for my cyanohydrine. So exactly the same as the previous guy. So second step, we will do a hydrolysis of my nitrile in alkaline medium to form COO- Na+. So far so good. Then the third step will be concentrated H2SO4 heat, and there will be 2 reactions that is taking place here. First thing is I'll have the reagents and conditions for elimination of alcohol to form alkene. So the 2-in will be there. And on top of that, since it is concentrated H2SO4, the condition is acidic. What you will be able to do is you'll be able to convert my COO- back to your COOH. So you notice if I consider option C, option D, which is pretty close, it's just that the sequence, which one do you want to do first, which one do you want to do later? Should you do elimination first followed by alkaline hydrolysis, or should you do the other way around? If you consider and you take the acid-base reaction of my COO- into consideration, actually D is a better answer, because if you hydrolyze this first in alkaline medium, yes, I'll end up with your conjugate base, COO-, but in the second step, when you're using con H2SO4, I can do both elimination and acid-base reaction at the same time. I can eliminate water to form alkene. I can also undergo acid-base reaction. I can protonate my conjugate base. I convert this back to our acid functional group. So in this case, if I compare option C versus option D, D is a better answer because I can get the exact product that we want. So answer to this question will be option D. Now question 26, the Ka values for 2 acids are given. We have ethanoic acid, Ka value is 1.75 times 10 to the power of minus 5. This is benzoic acid, Ka value is 6.46 times 10 to the power of minus 5. If I compare the Ka value, our benzoic acid is a stronger acid because it has a bigger Ka value. So we have 4 options. We want to decide which is the correct statement, and we will go through each one of them part by part. Now, since I'm comparing the acidity for carboxylic acids in organic chem, the concept that we should be using is the stability of conjugate base. So we understand that if I'm comparing acidity for functional groups in organic chem, we will focus on stability of conjugate base. If the conjugate base is more stable, then system will favor the formation of your conjugate base, which is more stable. That will mean that acid will dissociate more to give me the more stable conjugate base. It releases more H+, and the acid will be more acidic. So long story short, the more stable the conjugate base, the more acidic that weak acid. So that is the basis involving comparing acidity for my functional groups in organic chem. And if I consider statement A, Ka value for HCO2H is smaller than 1.75 times 10 to the power of minus 5, which is effectively the Ka value for your ethanoic acid. So this question is actually comparing the acidity for ethanoic acid versus methanoic acid, HCOOH versus CH3COOH involving statement A. We're comparing acidity involving these two guys. So concept-wise, we will look at conjugate base, and I'll consider the stability of conjugate base. Conjugate base of ethanoic acid is here. Methanoic acid conjugate base is here. The difference between them, for ethanoic acid, I have a donating group, which is CH3 group. So what this CH3 group is capable of doing is, since it is donating, it can donate electron to my carbon, and then effectively also push electron to my O-. It will intensify the negative charge on oxygen, and you actually destabilize this conjugate base, and if it is less stable, you make this acid less acidic. So we would expect ethanoic acid to be less acidic than methanoic acid. So your HCOOH is expected to have a bigger Ka value, not a smaller Ka value. So statement A is not true. Ka value for HCOOH is smaller, which is not true. Since it is expected to be a stronger acid, it should have a bigger Ka value than the Ka value for ethanoic acid. So A is wrong. Now, how about statement B? Now, statement B, what we have is Ka value for CH2Cl, COOH is smaller than 1.75 times 10 to the power of minus 5, but it is a bigger value than Ka value for CH2I, COOH. Now, what we do is we compare the first set, see whether this first portion is valid or not, because if it is not valid, then we don't even need to be bothered to look at the second comparison. Is it true that the Ka value for your chloroethanoic acid, it is smaller than 1.75 times 10 to the power of minus 5. Again, we're comparing against ethanoic acid. Conjugate bases are here. And you notice the differences between these two guys will be the presence of your chloro group. Cl group, it is a withdrawn group. What it will do is it will pull electron from your carbon, which will ultimately pull electron from my O-. And this guy, since it is a withdrawing group, it is capable of helping to disperse the negative charge on your oxygen, stabilize this conjugate base to a certain extent, and we will expect your chloroethanoic acid to be more acidic, and the Ka value involving your chloroethanoic acid is expected to be bigger than ethanoic acid itself. So it's expected to be bigger than 1.75 times 10 to the power of minus 5, not smaller. So therefore, the first portion of statement B is already wrong. Then the second portion involving comparing Ka value for your aldoethanoic acid is not necessary. So B is not true because the first portion is already wrong. How about statement C? Now, statement C, in a mixture containing equal concentrations of ethanoic acid and benzoic acid, the concentration for these two guys should be effectively the same. Now, of course, this statement is not true if I consider difference in strength. A stronger acid, by right, should be able to dissociate more to give me a higher H+ concentration, and if I can give more H+ concentration, it will also mean that the concentration of the conjugate base will also be higher. If there's a difference in strength, if I have the same concentration of both acids, the stronger acid will give me a bigger concentration of H+ and a bigger concentration of conjugate base. So statement C is also not true, and therefore D must be the answer. But let us try to talk about it. How do you know D is correct? Now, D is a bit interesting because we have to do a bit of figuring out. In two separate solutions of this compound, which involves a chloro group attached to benzene, a benzoic acid, with a chloro group attached to position 4, versus benzoic acid with the same pH, there will be a higher concentration of benzoic acid. So this is a bit interesting because usually when we compare acidity, we don't really compare in this way. But first thing we do is we compare acidity, who is more acidic, who is less acidic. We start with that first. Same thing, looking at stability of conjugate base. So if I have a 4-chlorobenzoic acid, conjugate base is something like this. Benzoic acid, the conjugate base is here. Cl group, same thing, it is a withdrawing group. It is able to pull electron from benzene, in turn, which will pull electron away from O-. It will disperse the negative charge on oxygen, help to stabilize the conjugate base. We will expect your chlorobenzoic acid to be more acidic, and you should have a bigger Ka value. Correct? So I will expect your chlorobenzoic acid, bigger Ka value than your benzoic acid. So far, so good. The next thing we do is, the question tells me, if I have two separate solutions and they have the same pH, which means that they have the same H+ concentration. And if I have a scenario where the H+ concentration of your chlorobenzoic acid is equal to H+ concentration of benzoic acid, then can I do comparison involving the concentration of these two acids? Now, actually we are able to do that because I can just use the formula involving the formula for me to determine H plus concentration, which is here. H plus concentration is equal to square root Ka times weak acid concentration, correct? So since the concentration of these two guys are the same, then H plus concentration for chlorobenzoic acid will just be square root Ka of chlorobenzoic acid multiplied by concentration of that same acid. Then this is also equal to H plus concentration of benzoic acid will just be the square root of Ka of benzoic acid multiplied by the concentration of benzoic acid. The square root actually is not important. I mean, we can remove them. But you notice, since this expression is equal to this expression, and we already know, or we have already deduced previously, that the Ka value for chlorobenzoic acid, it is a bigger value, and then the Ka for benzoic acid, it is a smaller value. In order for these two guys to be the same, then it must mean that I have a bigger Ka, therefore I must have a lower acid concentration. And if I have a smaller Ka, I will have a bigger acid concentration in order for these two guys to be the same, in order for H plus concentration to be the same. So this will mean that if I know that benzoic acid, it is a weaker acid, it has a smaller Ka value, therefore the concentration of your benzoic acid has to be bigger. And this is the reason why statement D is true. Again, it's a little bit interesting, a bit unusual for me to compare acidity in this way, but we can make use of this formula. For weak acid, H plus concentration is equal to square root of your Ka times weak acid concentration. Then we can do some manipulation, then we will be able to figure out statement D is correct. If the pH is the same or H plus concentration is the same, then the concentration of the weak acid should be higher. So answer to this question will be statement D. Question 27, what is produced when CH3NHCH2, CONH2, I have an amine functional group, I also have an amide functional group added to an excess of co-HCl aqueous. 4 permutations, let us try to figure this out. Now, since I have nitrogen compound, so the topic tested in this question will be targeting nitrogen compound. And since I'm also dealing with co-HCl aqueous, we only need to consider acid-base reaction. If I want to do hydrolysis, I need to do some form of heating. And if I only consider acid-base reaction, very simple, amine is basic, amides are neutral. Remember, the lone pair of your nitrogen on your amide is delocalized into your acid group, not available for donation. Amide is neutral. So the outcome is fairly straightforward. Only your amine will be able to react with HCl to form your ammonium ion, then with a Cl- as a counter ion. And if you look through the options, answer in this case will be A where your nitrogen, which is at position 3, is bonded to 2 hydrogen. Then overall charge of this guy, it is a positive charge, but the positive charge actually is on nitrogen, based on what I've drawn here. Then I have a counter ion, which is 1 Cl-. Now B is not true, because B is suggesting that the positive charge is on your amide nitrogen, which is wrong. That guy is neutral, so B is wrong. C is saying that both of them will undergo protonation, which is also not true, because this guy is the one which is neutral, so C is definitely wrong. D is saying that it is undergoing hydrolysis, and the product we're getting is an acid chloride, which is actually quite ridiculous, so D definitely is wrong. So answer to this question, very, very straightforward. It's just purely based on acid-base reaction. Recognizing that your amine, it is a base and amides are neutral, answer will be option A. Question 28, when treated with a catalytic quantity of H+, compound X decomposes into Y and Z. So information given here, Y actually carries 3 carbon, Z has 2 carbon, and X altogether has 5 carbon. So basically this is just somehow you need to break some bonds and split this into 2 different compounds, one containing 3 carbon and one containing 2 carbon. Then question tells me that Y and Z, both of them will turn hot acidified dichromate from orange to green. Both of them can be oxidized. Y reacts with alkaline aqueous iodine. It gives me a positive triiodomethane test. Z does not. Z reacts with sodium metal. That means there's a presence of your OH group. Y does not. Which other reactions will compound Y undergo? Effectively, I have to determine what is my compound Y. Then we can see whether does it react with Fehling solution, does it react with 2,4-dinitrophenylhydrazine. So let us take a look at this. Since ultimately the reaction with Fehling solution 2,4-DMPH is targeting carbonyl compound, that's why I say that this topic tested in this question is under carbonyl compound. And involving the differences between the reactant and the product, how can I chop your 5 carbon compound which is X, into 3 carbon and 2 carbon. Now, if you think about it, it's actually not that difficult for us to split the compound. It should be broken along this way that I've drawn here, because I need to split this guy into a 2 carbon compound and 3 carbon compound species. The logical way for me to do that is this 2 carbon, number 1 and 2, it has to be compound Z, and it carries the oxygen, and therefore when I break the CO bond, I have to break the CO bond this way, along this bond and along this bond. So therefore, this blue fragment will be compound Z, carries 2 carbon, carries 2 oxygen. Later we figure out the functional group, is it an alcohol, is it a carbonyl compound, and so on. Involving Y, you notice I have a 3 carbon compound, which is the yellow guy, number 1, number 2, number 3. Same thing, I'll have 2 oxygen. One is attached to carbon position 1, one is attached to carbon position 2. Later we will figure out, is it a carbonyl compound, is it an alcohol, what is the functional group. But at least we should be able to figure out, if I were to split X, which is 5 carbon, into 2 different fragments. One is containing 2 carbon with 2 oxygen, one is containing 3 carbon also with 2 oxygen, then the bond that we should be considering breaking is whatever that I've shown here. So it's not that difficult for us to do a bit of figuring out. The next thing is we have to identify the functional group. So first thing, it says that involving number 1, both Y and Z can turn hot acidified dichromate from orange to green. So both of them can be oxidized. Since dichromate is an oxidizing agent, if both of them can be oxidized, all the possible functional groups that we can consider, I can have an alcohol, primary and secondary alcohol, I can have an aldehyde, all these things are possible. Then involving number 2, Y reacts with alkaline aqueous aldene, which is a positive triidomethane test. Z doesn't do anything. Since it gives me a positive triidomethane test, the 2 possible structures that can give me this observation, either you have a carbonyl compound version, CH3, C double bond O bonded to an R group. Remember, Y carries 3 carbon, so therefore straight away I can draw. I know that Y has 3 carbon, it definitely has a CH3, C double bond O group bonded to a carbon. This guy or this structure has to be there. Or another possibility is I'll have a alcohol version, CH3, CHOH bonded to your carbon position 1. And we also remember that Y actually carries 2 oxygen, since we have already labeled this here. Okay, carbon position 2 will become C double bond O. How about your oxygen in carbon position 1? Would it be an alcohol? Would it be a carbonyl compound? What functional group this guy will be? Actually, at this stage, we are not so sure, but at least what I do know is, at least carbon number 3 is CH3, carbon number 2 is a C double bond O, only carbon number 1, which carries the oxygen. I don't know whether this guy is an alcohol or this guy is a carbonyl compound. Later we will figure out, but this is what we have so far, involving Y, correct? Then finally, involving Z, Z reacts with sodium metal, which means that there's an alcohol functional group, but Y does not, which means what? Which means that since Z undergoes acid-base reaction with sodium metal and OH group is present in Z, I can identify Z already, since I know that it carries alcohol functional group, and the only compound that can give me 2 carbon and with OH functional group will be 1,2-diol, CH2OH and CH2OH, which is consistent with the molecular formula for Z, C2H6O2. So therefore Z will be 1,2-diol, ethane 1,2-diol. Now how about Y? Now involving Y, since Y doesn't undergo acid-base reaction with sodium metal, that means I wouldn't have any alcohol function group present in Y. So based on the 2 possible structures I have previously, this one can be a carbonyl compound version, this one can be an alcohol version. We're going to reject the alcohol possibility since it doesn't react with sodium metal. Definitely this guy will be a CH3 C double bond O bonded to carbon with oxygen. Again, since carbon position 1 carries oxygen but it is not an alcohol, and therefore it has to be a carbonyl compound, which is my aldehyde. Again, if you try to figure out the molecular formula for Y, this is consistent with what we have here, C3H4O2. This structure involving Y is consistent with the molecular formula here. This is my compound Y, correct? So finally, if I want to run through which other reactions will compound Y undergo, since I have an aldehyde functional group, which is carbon position 1, it should be able to react with ethylene solution. And I also have carbonyl compound, both carbon position 1 and carbon position 2, both are carbonyl compounds. I have an aldehyde, I have a ketone. Both of them in principle should be able to react with 2,4-DMPH. So we will expect Y to be able to react with 2,4-DMPH also. So in this case, we will expect positive reaction for both reactant. Failing solution 2,4-DNPH. Answer to this question will be A. Question 29, we have vanadium forming a number of colored aqueous ions. So the species are here, the colors are here. They have different oxidation state. Later we will figure out accordingly. Question is asking what are the colors of the resulting solutions. If I have an acidic solution of VO2 plus, which is the yellow guy, reacting separately with excess of zinc metal and excess of tin metal. And I have 4 different permutations, and we will see what is the final solution, what is the color of the final species. The topic tested in this question is fairly straightforward. It is under electrochem. Determining the feasibility of the reaction basically is to determine what is the extent of the redox reaction. Since you're throwing in metal, zinc metal, tin metal, metals undergo oxidation and therefore they're reducing. And if you have vanadium species VO2 plus, and if you figure out the species here, my VO2 plus, which can undergo reduction, VO2 plus, the yellow guy, can be reduced to VO plus 2 charge, which is the blue species. All these values are in the data booklet, we can refer to that. Then the blue species can be further reduced to the green one, V3 plus. The green one can be further reduced to V2 plus, which is the violet species. So basically, I know that when a metal undergoes oxidation, it is going to reduce the yellow vanadium species. What is the extent of the reduction? Does it reduce this to the blue guy? Or does it reduce this to the green guy? Or can it reduce it all the way to the violet species? Correct? So what we are doing is we are determining the extent of the redox reaction by calculating E cell, basically. So all the E values, we have them here. And involving the E cell calculation, if I calculate E cell, which is E reduction minus E oxidation, as long as your E cell is positive, reaction is feasible, then we will expect the reaction to take place. Then we will consider the next stage. So let's talk about it part by part. First thing is I consider the redox reaction between zinc and the yellow species, VO2 with a +1 charge. Reduction of your vanadium species, E value is +1.00, minus oxidation of zinc, E value it is a minus 0.76 volt. End up with a positive value. E cell positive, reaction is feasible. So I will be able to reduce yellow guy, reduce it to the blue species, VO plus 2 charge. Correct? I know that this guy appears in the next step. I have to consider whether this guy can be reduced further to the green guy. What I'll do next is I'll consider the feasibility for the reaction between zinc and the blue species. So it's another calculation, very simple. Reduction of the blue species plus 0.34 volt minus the oxidation of zinc, another positive E cell, another feasible reaction. So the blue species can be reduced to the green guy, form V3 plus. Then we have to consider a V3 plus, can it be reduced even further to the violet species? Another E cell calculation, reduction of V3 plus minus 0.26 volt minus oxidation of zinc minus 0.76. I have another positive E cell, reaction again feasible, and therefore this guy can reduce your vanadium all the way to V2 plus to form your violet color. So final color involving zinc, it will be violet because zinc, it is reducing enough to reduce your vanadium all the way from the yellow guy to the violet species. So vanadium can go all the way, since all the 3 stages, the reaction is feasible. Now, how about tin? Tin idea is the same. You just keep on calculating until we end up with a negative E cell. Involving tin, the half equation that we should consider is tin to tin 2 plus. E value, it is a minus 0.14 volt. So basically the calculation is the same, the idea is the same. First thing I consider, can tin reduce your yellow species to the blue one? Correct? So I consider oxidation of tin and the reduction of the yellow species, reduction of your VO2 plus 1 charge, plus 1.00 volt, minus E value for tin, minus 0.14, positive value, reaction feasible, VO2 plus can be reduced to VO plus 2 charge. The yellow species can be reduced to the blue guy. Then stage 2, can the blue species be reduced to the green one? And I calculate E cell plus 0.34 volt, involving the E value for your VO2 plus, minus oxidation of tin, which is negative 0.14 volt, end up with a positive value. So this guy can reduce your VO2 plus to V3 plus. I can form the green species. Finally, calculating the E cell involving V3 plus and tin, whether this redox reaction is feasible or not. I'll have a minus 0.26 minus negative 0.14. Then this finally I'll have a value which is a negative E cell and therefore this reaction is not feasible. Tin is not capable of reducing V3 plus to V2 plus, and therefore it just stopped at V3 plus. Final color involving tin is expected to be green. So therefore, answer that we will have with zinc, final color should be violet. With tin, final color should be green. Answer to this question should be D. Alright, the final question for this exercise involving question 30. Now question 30, the atomic radii and the first ionization energies of the metals, iron and cobalt are very similar, despite the fact that cobalt has a higher nuclear charge than iron. So which statement explains one of these similarities? So we have 4 options. Later we will run through each one of them. Now, the topic tested in this question obviously is involving transition metal. And when you try to locate these two guys, they're just next to each other. Involving iron, the atomic number is 26, cobalt is just 27. And this is actually an important concept involving transition elements, because if you notice what we are doing for transition elements, we are focusing a lot on the similarity involving my transition elements because of this idea here that we are using to try to answer this question. So across the D block, from scandium all the way to zinc, you notice the proton number increase. So yes, therefore the nuclear charge will increase. And I'm adding electron to an inner 3D subshell because all of them is 4s2 3D something. Scandium is 4s2 3D1, titanium is 4s2 3D2, vanadium is 4s2 3D3, and so on. So when I'm adding electron to an inner 3D subshell. Shielding effect actually goes up. The inner 3D electrons, since they're closer to the nucleus than my 4s electron, they're able to shield your 4s electron to a certain extent. So it turns out that the increase in the nuclear charge and the increase in the shielding effect will cancel. And since they cancel each other, the effective nuclear charge across my transition element, across the D block, will be similar. And the consequence is, since I have similar or invariant effective nuclear charge, overall attraction between the nucleus and the valence electron is the same, energy required for me to remove the electron is the same, so therefore I will have a lot of consequences and a lot of properties, things like ionization energy, things like the size, things like polarizing power, and so on, will be similar. So the consequence involving transition elements, they will share many similar physical properties as well as chemical properties because of this very, very simple idea here. Increase in the nuclear charge and increase in the shielding effect because I'm adding electron to the inner 3D subshell. These two effects will cancel each other. Effective nuclear charge across the D block is roughly the same. So the physical properties and many chemical properties will also be the same, i.e. sizes and so on. Okay? So with this in mind, let us run through the options, see which one of them is the best answer. So involving A is saying that atomic radius of cobalt is similar to iron because 4s electron causes the same shielding in both atoms. Now, this is a bit weird because if I consider 4s electron, they are my valence electron, they are furthest away from the nucleus, they don't block anybody. Only inner shell electrons can shield valence electron. Valence electron, they cannot shield each other, they cannot block each other. A is definitely wrong. Since they are valence electron, they are not able to block any other electrons in the same principal quantum shell. So A is wrong. Now how about B? B, atomic radius of cobalt, similar than that of iron because cobalt has extra 4p electron, which is increasing the shielding effect. Now, if you consider the difference between iron and cobalt, iron, if you write out the electronic configuration, will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. So what is the difference? The difference is between 3d6 versus 3d7. Where are my 4p electrons? There are no electrons in my 4p subshell. This is 4p0. The other guy is also 4p0. The electrons is not added to my 4p subshell. So B is also totally off. If you consider the electronic configuration for iron, electronic configuration for cobalt, this statement B is totally not relevant, totally not valid. So B is rubbish. We don't consider that. Correct? How about the next one involving C? C, first IE of cobalt, similar to iron because my 3D electron is being shielded by 4s electron. Now again, your valence electron is 4s, furthest away from the nucleus. I cannot use valence electron to shield inner shell electron. It is the other way around, correct? So in this case, since my 4s, it is a valence electron, I cannot block anybody, I cannot shield any electrons. Definitely, I cannot shield 3D electrons that is closer to the nucleus than 4s. So C is definitely wrong. Finally, D. First IE of cobalt is similar than that of iron because my 4s electron is shielded by an extra 3d electron. Now this makes a lot more sense. Again, if you look at electronic configuration, iron versus cobalt, iron is 3d6 4s2, 6 3d electron that act as a shield to block my 4s electron. Cobalt, I have 3d7 4s2, one more 3d electron. Remember, 3d electron is inner shell electron, and therefore it is able to shield my 4s electron more effectively. So in this case, answer should be D because cobalt has one more proton. Nuclear charge increase. Add one more electron to 3d subshell, shielding effect also increase. These two effects will cancel out each other. Overall, effective nuclear charge between these two guys are essentially the same. Overall attraction between nucleus and the valence electron between these two guys are roughly the same. Therefore, first IE for cobalt and iron will be similar. So the answer to this question will be option D.